Hello. In this video we're going to be talking about bases. So this is another review video, so I expect you to already know this stuff. We're not going to be proving any theorems, but I do want to go over what I expect you to know about this. So to start out with, we have a definition of what it means to span. So start out with, we have these vectors. We're taking the span of them, which is the set of all possible linear combinations where the coefficients are in R. Okay? We might at a later point in time replace R with C in case we're dealing with complex vector spaces instead of real vector spaces. Okay, so we say that this subset that we're talking about spans the subspace U of V if U is equal to the span. Okay. A subset, so another definition here, a subset B of V is called a basis if B is linearly independent and it spans the entire space. So here we're treating V as this subspace of itself. Okay, so those are our two definitions, and now we're going to look at some theorems. Okay, so here are the first two theorems we're going to look at. This first one is both a theorem and a definition. So V is a vector space, and the theorem says every basis for V has the same number of vectors. Okay, and then the definition part of this theorem says that we're just going to call that number of vectors the dimension of V. Okay, and we're going to denote it dim V. So I'll be using that notation both later on in this video and throughout the rest of the term. Okay, our next theorem says if we have a subset S of V, any two of the following imply the third. So the first one is S spans V, second one is S is linearly independent, and the third one is the size of S is the dimension of V. In other words, S has the correct size to be a basis. Okay, so just to note, any two of these imply the third. If you look at the first two, if you have both of these things, it implies this. It implies that the size of S is the dimension of V. And that's exactly what this theorem says. Okay? But we still needed that theorem in order to define what dim V was. So if S spans V and is linearly independent, that means it's a basis. And therefore its size is this thing that we're calling the dimension of V. Okay? But it's also true that if S spans V and it has the size of the dimension, then it must be linearly independent. And the third thing that this theorem is telling us is that if S is linearly independent and it has the correct size, then it must also span. All right, here are two more theorems that I want you to know. So this first one says if we have a subset of V which is linearly independent. By the way, before I get into this, I'm being a bit lazy here with both of these theorems, and I'm not saying let V be a vector space at the start. It's assumed that V is a vector space for these theorems. I'm just being lazy. If we have a subset of V which is linearly independent, then we can complete to a basis. So complete to a basis means that there are some extra vectors we could add to this set onto the end so that we get a basis for V. Okay, so if we have something that's linearly independent but it's not big enough to span the whole space, then we can find vectors, they have to exist, to add on to the set so that we eventually get to a basis. Okay. This next theorem here is sort of the opposite theorem. It's saying if we have too many, but they span, so if we have a subset of S and it spans V, then there are some which we can remove. So we remove some and get a subset T, and T is now a basis for V. And here's the first point where I should really point out my notation for subset looks like this. This does not mean proper subset. So my proper subset notation looks like this. If I want to say that A is a subset of B, but is not equal to B, I will actually put a not equal to sign below the subset sign. Okay? So this right here does not exclude T from being equal to S. That's perfectly possible. All right, thank you for watching.